Okay, so if you're watching this from home today, we're going to start looking at mechanical energy. And so when I think of mechanical energy, you might think of someone working in a garage or something like that, like a mechanic. That's not at all what this means. Mechanical energy is just a way of classifying various forms of energy. We can break energy down into two different subsets. One is mechanical, the other is non-mechanical. Let's take a moment and look at some non-mechanical forms of energy for just a few. So we could say non-mechanical forms. Things like chemical potential energy would be what we consider non-mechanical forms of energy. When you ate breakfast this morning, that energy, that food that you ate, you can break that down and use that to be able to do some work there. That's called chemical potential energy. It's from your food, measured in calories probably. That would be a form of non-mechanical energy. Another one could be thermal energy, sometimes called heat energy. So take your hands, rub them together. When it's cold outside like that, you're going to generate some heat as a byproduct. That's considered non-mechanical forms of energy. We have some more. You split an atom, and you use some of that energy from that fission to be able to run a power plant or something like that. It'd be considered nuclear potential energy. That's non-mechanical in form. And then, my gosh, how many of you guys were outside on Saturday and enjoying the sunshine? Pretty nice out there. We might call that radiant energy. And so radiant energy from the sun, these are all considered non-mechanical forms. What is mechanical? It has to do with energy associated with large moving objects. So objects that are large in size, things like basketballs, bowling balls, cars, things like that. Energy associated with large moving objects and stored energy that could cause large objects to move. So when we talk about mechanical energy, we're not talking about mechanics working in the garage. We're talking about the forms of energy that we're going to study today. Large moving objects or stored energy that could cause large objects to move. Large just means bigger than atoms. So if I'm talking about something that's on the macroscopic scale, something that we'd work with in the classroom or out in the basketball court or anything like that, it would be larger than atoms. It would be mechanical energy forms. Now we're going to look at two forms today, and then the other form we'll look at. We're going to look at these today. We're going to look at kinetic energy, and we're going to look at gravitational energy. Tomorrow we'll look at elastic. Okay, elastic's a little bit harder to quantify, but today we should be able to get through kinetic and gravitational without too much difficulty. Kinetic energy, objects that are moving. Anything that's moving has the ability to do work on other things because of its motion. So if it has the ability to do work, we'd say it has energy. How we define it, it's equal to the amount of work it can do as it exerts force while stopping. So if something is moving, it's going to take force to stop it. Well, how much force it exerts while it's stopping through that distance is what we would call kinetic energy. How we quantify it. This equation you may have seen before. It's energy associated with motion. I tend to use the symbol Ke as opposed to E sub k. Doesn't really matter which symbol you use, but we take 1/2 the mass of an object multiplied by its velocity squared. It looks very similar to momentum. So I want to take a moment and write down momentum for a second. You may recall that momentum was equal to m times v. And something that we should pay attention to is that momentum and velocities are vectors. I mean, they have direction associated with them. I notice that kinetic energy has the exact same kinds of quantities in it, except kinetic energy is a scalar quantity. It has no direction. So even this is a vector, meaning it has direction associated with it. And this is technically what's called a scalar, which means it has no direction. Doesn't matter which way it's moving. Its energy doesn't depend on which way it's going. Okay, so again, directional quantities can often be difficult to work with. Now, something that's important between these two is that this one has a velocity in it, this one has a velocity squared. The fact that it's squared means it has a pretty significant impact on that value. We would say kinetic energy increases with the square of the speed. The idea behind that, something that's traveling twice as fast would have 4 times the kinetic energy. So doubling your speed will quadruple your kinetic energy. Or you go 3 times faster. So instead of going 20 miles an hour down the residential street, you're going 60 miles per hour down the highway. How much more kinetic energy? That would increase your KE by a factor of 9. So you have a really big dependence on speed. Stopping distance is also proportional to KE, so you're going to need 4 times the distance to stop if you're traveling twice as fast. So you're on the highway, traveling 60 miles per hour, it's going to take you 4 times further than if you were traveling 30 miles per hour. And it's just because of that dependence on speed squared. Raise your hand, you've been through a driver's training class? They usually ask this kind of question, right? They want to make sure you understand that speed, they often say speed kills, right? Like the faster you're going, the more likely it is that you could be in a serious accident. But you also, if you're going to stop your speed, you're going to need quite a bit more distance to stop if you're traveling faster. This diagram up here, upper right-hand side, is from your 8th grade book. You may remember taking physics in 8th grade, maybe in 7th grade, but this is just showing the stopping distances based on your speed. So if you can stop a certain distance, traveling 50 kilometers per hour, it's going to take 4 times the distance if you're traveling twice as fast, and 9 times the distance if you're traveling 3 times as fast. Okay, so again, strong dependence on speed. You're going to need some calculations here, right? So you have to be able to work with this formula. We have a car traveling 10 meters per second, 1,200 kilograms of mass, and in this case, it's traveling up a hill. I just like to know its kinetic energy. So it's energy associated with motion. We take 1/2 mv squared, and it's really not too bad to do. Sometimes people will forget to square it. Other times people will think that they're squaring everything. The only thing you're squaring here is the speed. So when I do that, make sure that you're I would start with your 10. Right? I'd start with 10, square it, then multiply that by 1,200, and then take half of that. Okay. So again, just make sure you can do that calculation. Try it really quick. Many of you have calculators on hand. Once you have that, if you would, just shout it out. Make sure that I'm doing it correctly. I'm getting 60,000. Anyone confirming? Okay. So again, 60,000. And then the unit for that, my gosh, it's a form of energy. It should be the same unit as work. And so we would say that it's 60,000 joules. Energy associated with that car's motion, 60,000. Now, cheetah, fastest land animal, can reach speeds of about 60 miles per hour. It's 27 meters per second. Its mass is 75 kilograms. How much KE does it have? Try that calculation. Just make sure you can do it. Again, it's going to be a smaller mass, but traveling faster. So both of those factors come into play. Do a quick calculation there for me. I'm getting roughly 27,337 joules. Confirming? That's almost half of that car's kinetic energy. And you might say, my gosh, that cheetah is only 75 kilograms, the car is 1,200 kilograms. It's the dependence on speed. You notice that cheetah is traveling a lot faster. I'm squaring that, so it becomes a really big value. Do not use your calculator for this one. For the runners, try to do this without a calculator. Try to do it without a calculator. You notice I have 75 kilogram runners. So each of those runners has the same mass as that cheetah. They are running at 3 meters per second as opposed to 27 meters per second. Can you reason through how many of those runners I would need? Moving on, let's say that we have a group of runners. How many of them would I need to have the same kinetic energy as that single cheetah? See if you can do that without a calculator. If you have to, can't figure out how to do that, then go ahead and use that calculator. But some of you are going to reason through how you can do it. Okay, see if you can try. Give it a go. Once you have a number, I'm going to have you write it down, the number that you have, circle it. I want to see how that looks. So again, I'm getting a sense as to whether or not you're able to do this without using a calculator. If you have to, that's fine, but once you have it, circle it. Thank you. That's okay. Yeah, I see a lot of people having the same number. And it seems to be off a little bit. That's okay. That's all right. Yeah, I see the most common answer that I see up there is 9. The most common answer I see is 9. It's not 9. And the reason it's not 9 is because speed is squared there. So let me try this one. How many times more speed does a cheetah have than the runner? How many times more speed? 27 is how many times greater than 3? 9. But because speed is squared, 9 squared is 81. I would need 81 of those runners to have the same kinetic energy as the single cheetah, and that's because that depends on speed. Now, for those of you that are sitting there going, how do I, if you want to use the numbers, if you want to do the numbers this way, you can, but I wanted you to see that this number there and that number there are different by a factor of 9. Because speed is squared, that means that that cheetah has 81 times the kinetic energy of a single runner, so I need 81 of those. Now, if you want to do it this way, you can. You can say 1/2 75 times 3 squared. If you just want to go through and do that, you can. That number is 337.5 joules. So I would take this number, 27,337, and divide that by 337.5, and sure enough, you should get about 81 runners. And again, it might not be exactly that because of rounding, but that's the way you go through and do it. Okay? All right. Give you guys a little problem there down at the very bottom. A baseball player can throw a ball, let's say, I want to determine how fast you'd have to throw that baseball so that it has the same kinetic energy as a bowling ball. So a bowling ball might be thrown down the aisle and has 67 joules of KE. What I'd like you to do is see how fast you'd have to throw that baseball to get it to have the same kinetic energy. I want to give you a go at that. See if you can do it. The way you would set that equation up would look something like so. You might not draw these pictures here. If I'm going to throw a baseball to have the same kinetic energy, its velocity is going to end up having to be really large. And the question is just how large would that number be? So you got to take that baseball's mass, try to figure out the velocity for its kinetic energy to be 67. Okay. So again, 67 joules would be equal to 1/2 the mass of that baseball. Do you guys agree that 146 has to go in as 0.146? I had to make sure the units are correct, so I can't put in 146. That has to be 0.146. Can you solve that equation for V? If kinetic energy is proportional to the speed squared, can I set up that equation and then solve that for V? Give that a go. See if you can work through that magic to get that value for velocity. Once you have that number, again, I'm walking around checking to make sure that the quantifying of things that people can do this kind of math. Circle that number. I'd like to see what you have for that velocity. Give it a go. Give it a go. you just throw some units on it. Or just throw some units on it when you're done. Okay, I'm seeing at least a few of these things to be done correctly. I'd multiply both sides by 2. That's 134 is equal to 0.146. I'd divide both sides by 0.146. And b would then be equal to the square root of that number. So 134 divided by 0.146, that's 917-ish meters squared per second squared. And when you take the square root, you get about 30.3. And so how fast is that in miles per hour? Let's try that. 30.3 divided by 0.447. That's in the neighborhood of 68 miles per hour. That's definitely possible. So if you want to have that baseball have the same kinetic energy as that bowling ball, you just need to throw it about 68 miles per hour. Okay? So quantifying KE. Any questions on that? All right, we have another form of mechanical energy. The other form that we want to look at is something called gravitational potential energy. And so this is the first time we've studied PE stuff. So KE is energy of motion, PE is energy of position. So any kind of positional energy is what we call potential. So potential energy is positional energy. Where is that object located within a system? So just like momentum involved systems, potential energy is associated with systems of objects. It can be considered stored. And the reason we say it's stored is it is recoverable. It has the ability to do work or to transfer energy as its position changes. Probably the most common form of potential energy is this thing called gravitational potential energy. So Ava's going to help me with this really quick. Put your hand out. I'm going to drop this thing to you. Okay, so this thing has energy associated with Ava's hands. So as I lift this thing up, would you guys agree I'm doing some work as I lift it up? I'm storing that work in its position. So I'm going to allow that to drop. And sure enough, as that thing drops and takes its energy of position, it converts that into energy of motion. You can sort of feel that. Now, if I double the height, how much more work did I do if I double the height? So instead of lifting it to there, I lifted it to there. How much more work did I do? Twice as much. It's mgh, right? It's work times distance. So if I double the height that I lifted, I'd actually do twice as much work. So that amount of energy that it has is twice as great. What if I triple the distance? It would have 3 times as much energy, right? So the idea there is that gravitational potential energy has to do with position. It is, we symbolize it as GPE. Belongs to a system. One is maybe that ball, and the other is the Earth. So the Earth has to be a part of that system. The Earth is that object that exerts that force on it to be able to give it that energy. So it's equal to the amount of work done to lift an object within a gravity field. So if I lift that thing up on Earth, a certain position, I have gravity sort of pulling it down. I can store that work as GPE. Now, as an equation, I want to go back through to look at how we define work again as force times distance. And in this case, the force is the weight of that object, and the distance is the height that I'm lifting it. So when you start looking at how to quantify gravitational potential energy, zoom in for you so you can see that better. Again, force weight is equal to m times g, and distance here in this case is height. How high am I lifting it? So we would say the gravitational potential energy is equal to m times g times h. It's gravitational PE associated with that position. And again, we can classify that with this equation here. It's again, an equation you may have seen it before. It has to do with the mass of an object, what the acceleration due to gravity is, and how high up I'm lifting it. So here you double the height, you don't get 4 times the energy, you get twice the energy because of that dependence on height. It's not height squared. It's just on that height. Okay, so GPE equal to mgh. Make sure the mass is in kilograms, G is in meters per second squared, and H is in meters, and then you can quantify energy that way. Okay. Two forms of energy today. One is KE, 1/2 mv squared. The other is GPE, mgh. Let's go ahead and just do a couple of quick calculations here. Make sure we're familiar with how that works. Pun intended. Wrecking ball, 125 kilograms, about 4 meters above the Earth. I'd like to know how much GPE the ball has between the position and the Earth's surface. So again, anytime I'm doing GPE calculations, I'm going to measure that height relative to some zero level. Take that 125 kilograms. You know what? I'm gonna use G as 10 so that it's easier for us to be able to do these calculations. Instead of 9.8, just make it 10. It's close enough. We can go with that. And then height would be 4 meters. So again, the energy associated with that position depends on where it is in that gravity field. So I take 125 times 4. That's 500, multiply that by 10, and that's about 5,000 joules. Energy associated with that position. Now, quick question for you. See if you can concept-based question. If I were to cut that chain right here and just allow that ball to fall, it's going to fall down to the Earth, and it's going to leave a crater in that Earth as it exerts force on the Earth to come to a stop. My question is how much work could that wrecking ball do on the Earth when it falls? And that answer should be 5,000 joules, because that's its energy of position. So the amount of energy it can actually, how much work it can do as it hits that ground is equal to its gravitational potential energy it had. So that would be 5,000 joules of work that's doing. I want you to try Carlos's 6 books on his bookshelf. Each weighs 17 newtons, and they're 2.3 meters from the ground. I'd like you to try to calculate for me how much GPE those books have relative to the ground. Okay, give that a go, see if you can do it. My question I have for you as you go through and do that calculation is that 17 newtons. What does that represent in that equation? And don't say it's the mass, because it's not the mass. That 17 newtons represents the mass and the acceleration due to gravity. Those two things are the same value, and how I know that is that it's measured in newtons, not in kilograms. So I have to be careful there. I'm not going to multiply that 17 by G, because I've already have that G in there, right? So you have to look at those units for that. They weigh 17 newtons, so that's their combined mass times G. Now I have 6 of those. So when I go through and do this, I'm going to say it's 6 times 17 newtons. And then 2.3 meters. And I don't have to multiply by G either, okay, because that 17 contains it. And that number is 200 and 34.6 joules. Raise your hand. You have a bookshelf in your, maybe in your bedroom, something like that. Bookshelf. Few people. Carlos was he was a student of mine about 15 years ago. So when I wrote this question, it was sort of in his honor. He was like, "Mr. Isaac, I'm sort of a slob." He goes, "My books are always on the ground in the room." And so he would say his mother would come in and say, "Carlos, pick those books up, put them on the shelf." My question for you is, how much work would Carlos have to do to take those books from the ground and stack them on the shelf? How much work would he have to do? And that would be the number. That represents the amount of energy it takes to lift those books up and store them. Earthquake comes. Raise your hand. You've ever been in one? Earthquake comes, knocks those books off the shelf. They fall off the shelf and land on that little K'NEX toy that he had built in his bedroom on the floor. How much work could those books do on the K'NEX toy as they fall? That much work. That energy is associated with the position of those books. It takes energy to move them there, and those books can give that back when they fall down. I want you guys to try the one off to the right, number 3, all on your own. See if you can do it. How high must that platform be so that a 56 kilogram diver would do 2,300 joules of work on the water as he falls? So he's going to jump off that platform, fall into the water. I want to know how high it has to be for him to do 2,300 joules of work on that water. Give it a go, see if you can do it. Circle it. I want to walk around and see if I'm seeing this correctly. Right. So just give me a circle. If you use G as 10, it makes the math a little bit easier to do. If you use G as 9.8, your number would be slightly different. And folks, we're about done, so I want to give you some class time to work on some things. That bottom question, number 4, see if you can figure out that one as if you're already done with the other one. See if you can figure out number 4. I'm seeing a lot of the correct answers for number 3. I'm going to go ahead and put that solution up. In the event that you didn't get it, you can see this here. That's math, so I have to multiply that by G. I'm going to make G be 10. And so that'd be 2,300 divided by, that's 560. And I'm getting about 4.1 meters. So that platform would have to be 4.1 meters up in order for that person to be able to do that much work on that water. If you use 9.8, and I think I did see a couple of people do that, and you see it's not that big of a difference. I'm getting about 4.2 meters. So again, very small difference between those, so G is 10 is fine. Last question there. This is really just asking what is the potential energy of that ball at each of those steps? And if it's 50 up here, and it's 0 down there, could you tell me what it is on each one of those steps? And you might notice that because each of those steps are the same height up, that number 50 is going to turn into 40 here, 30 there, 20 there, 10 there, and then 0 there. So all that staircase is really just taking that energy and dividing it into 5 little equal intervals. Okay? And so gravitational potential energy. Questions for me at all? It's a fair number of calculations. You have to be able to work with them because we are going to quantify efficiency of your launcher. So when you build your launcher, you're going to say, how much energy did I store in that? How much energy did I get out? One of those forms of energy is gravitational potential energy, how high it goes. The other one is its kinetic energy, how fast is it moving. So you have to be able to quantify it. I'm going to go ahead and stop there. You have a good 12 minutes, and I wanted to make sure